All right, so a few administrative things before that. I don't know if I mentioned it yesterday or not, but as far as the service learning project, group sizes of 3 or smaller. Okay, if you want 3 people, 2 people, or if you want to work alone, you can do that without asking me about it. If you decide you want more than 3 people in a group, let me know and we'll talk about if that makes sense, if the project is the type of project that can be split into 4 or 5 or 6 different pieces in a logical way. But if it's 3, 2, or just one person working alone, you can fine to do that. You don't have to talk to me ahead of time. There's a Discord channel now for the SLP. If you're on Discord, you've already noticed it. But it's again, it's an unmoderated channel. It's for student use. I'll peek in once in a while, but I'm not really participating actively. But basically, it's a place you can kick around ideas for service learning projects. You can, put a call out. Hey, I got this idea, but I need somebody who understands auto mechanics. Is there anybody who wants to work on or talk about an SLP involving that, right? So it's just another resource that you can use. So that's up and running. The other thing is there is an extra credit opportunity. Okay, there's an engineering and computer science club meets Friday afternoons at 12 in room 126. Starting week 3, we're in week 2 right now. So starting with week 3's meeting, we are going to allow students who are working on their SLPs to come in and present to the club a short 5-minute pitch on their project. Okay, this is a really good exercise, one, for getting some practice on formulating your ideas of what your project is and talking about it, which is what you're going to be doing at the expo at the end of the quarter anyway. And 2, a few points of extra credit for participating. There's a sign-up sheet in the collaboratorium. If you go in the first set of doors, immediately to the right on that window, there's a tape-in sign-in sheet with all the different dates, and you can pick a time slot to present. If you're in 215 this quarter, you have class at 12:30, so that kind of crunches down on your time slot. But if you wanted to do that, right, you can slip out for 10 minutes to do a presentation, as long as it's not the day of the midterm or something. Yeah?
Is 2 points per meeting, or is it total 2 points?
I got to figure out how many points it's going to be extra credit. It'll be a few points for going and presenting your SLP, right? Not just for going to the club meeting. But it's for going and giving a 5-minute presentation of what your idea is for your service learning project. Does that make sense? All right. So let's look at the current one-day project. So this is 407, and this is probably the last ODP for a few days. I don't think I'm going to post one for to start tomorrow morning. So 407, it's another shell script, okay, and this one has some very peculiar instructions, and there's a demo that shows you exactly what it should do, but I'm going to basically run through a sample of what your program should do here. But if you want to see it again, you can look at a demo. So you run your script, it prints out a number sign. Okay, just a number sign, no extra spaces, no extra prompts, nothing. 1 character, number sign, and it waits for the user to type in something. Okay, if the user types in a 1 or a 2 or a 3, okay, followed by an enter key, it should print out the words OK and exit. Okay, OK, print out a new line, exit the program. So this is checking how many sticks you want to take in PA1, right? It's another snippet of your full programming assignment. So it prints out a number sign. That means user type in a number. If the user types in a 1, 2, or 3, it says OK, and the program exits. If you type in anything other than 1, 2, or 3, it prints out ERR, which means error, and then it prints out a number sign and waits for another input. And if you type in a 1, 2, or 3, it says OK. Otherwise, it prints out the word fail and it exits. So again, this is the part where you're asking the user how many sticks do you want to take, and if they put in a legal number, your program will continue. If they put in an illegal number, it gives them 1 chance to try again. Okay, but instead of saying, hey, you're cheating, try putting in a legal number, it just prints out ERR. Okay. And then if you put in a legal number, everything's fine. If you put in an illegal number a second time, it says fail and it exits. So let me show you what this looks like in action. So I run my script, there's the number sign, it's waiting for me to type something in. I type in a 1 or a 2 or a 3, it says OK and exits. So that's one test case. Next test case, it prints out a number sign, I put in something crazy like a 4, it says ERR. I put in a valid entry, it says OK. Third test case, you put in something crazy like a 55, it says ERR. You put in something else crazy like a 66666, and it says fail. And those are the only 3 things that can happen when you run this script. Either your first number was good, it says OK, your first number was illegal, your second number was good and it says OK, or both numbers were illegal and it says fail. Does that make sense what the behavior is? Okay, and we're going to do some pseudocode to look at how we can do this algorithmically. It's basically a bunch of nested if statements. And what you write here, you can pretty much take and plop in somewhere in your PA1, because this is something that happens every time you ask the user what their move is going to be. Same kind of dialogue. All right, a few general comments on ODPs from conversations that I've seen in Discord. It does not matter what you name your ODP within reason. Okay, if you happen to call it something that's already a reserved word, like if you called your ODP GCC, it's probably not going to assess correctly, because GCC is how we call the C compiler. Okay, if you call it test, it's not going to assess correctly because test is a built-in keyword. If you call it script, that's another built-in command. That's not going to assess correctly. But you will notice these things generally when you try to run these from the command line. Okay, so if you write your program and it does stuff, and I try to assess this, and I say grade, and I get errors and I get a 0 out of 10, right? Before you start trying to figure out what's the problem here, make sure that you've tried running your program without assess, right? Because if I try to run my program just from the command line, I get a really simple error message, permission denied. I forgot to change it to be executable. Okay? But you should notice that because you should thoroughly test your program from the command line before you run assess. And I'm seeing lots of people trying to assess and trying to figure out why they're getting 0 out of 10, and their program does not work from the command line. Right? And you're going to save yourself a lot of time if you try to debug the program yourself, and then when you're really sure, not just that the code looks right, but that you've actually run it with different test cases, like we just did for ODP 407, and you're really sure that it's doing the right thing, then go ahead and throw it into assess. And it'll be a much shorter debug cycle from that point to the end. Make absolutely sure that you have this, and it's got to be the first thing in your script. If you put your name before this, your script's not going to assess correctly. Okay? Because assess is running as a Java program, and it's not using bash natively when it runs your script. So it's got to find this in the first line to know that you're supposed to use bash. Otherwise, things like if statements and stuff don't work correctly, and you get errors. And you have no way of knowing that. You just see 0 out of 10 on your grade. So make sure that number sign exclamation mark is the first thing. Make sure that the script is executable. Right? So one time after you create the file, do the change mode 755 to make it executable, and make sure it's not a weird reserved name. And if you call it ODP something, it's not going to be a reserved name, and it's easy to keep track of what the program is. Because another really common mistake is assessing the wrong program. Right? You have a program that you wrote for yesterday's ODP, and you repeatedly keep trying to use that for today's, because you just called it program or something, right? And that's really hard to debug because you look at the code and it looks right, but that's not the one that you're actually feeding in. So I think those are the biggest gotchas that I see people running into. All right, so let's review what PA1 is going to do. It's a game called Stick. You run this, gives you a welcome, says how many sticks do you want to play with, and we'll play with 30 sticks. Okay, who should go first, user or computer? And this has got to be a legal entry. If it's not a legal entry, just keep asking. There's no timeout. There's no limit to how many times they can put in the wrong answer. Keep asking until they put in either a U or a C. Okay, so I'm going to say U for user. There's some instructions. Print out the initial pile of sticks. This was yesterday's ODP, right? Print out the pipes with a number in parentheses. How many sticks do I want to take? I'm going to take 2 sticks. Print out the new pile of pipes. Computer says I take 1 stick. Now there's only 27 left. And I'm going to take 3, the computer's going to take 1, there's 23 left, and I can hear the computer sweating because I'm going to take the last stick and I'm going to win. Okay, and if you take an illegal number of sticks, that's cheating, try again. Pick a legal number, everything's fine. Take an illegal number of sticks and try to do that 2 times in a row. That's your fail condition, kicks you out, game's over. Okay, so that's today's ODP. That's where that goes in. So let's think about, from a high level, how do we tell the computer to do what we just saw? And I'm going to write what we typically call pseudocode. Pseudocode, or P-code it's called sometimes, is code that kind of looks like C or Bash or something like that sometimes, but it's really not. Okay, it's not. If we were writing pseudocode for C, we probably wouldn't say integer I semicolon, right? We would just start using I, and that won't compile. Okay, but this is not code that's meant for the computer to see. This is meant for us, and it's generally higher level than, you know, C code, scanf parentheses blah 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 %sign ampersand, stuff like that. That's the C code, right? We want to be at a higher level than that. What we're trying to capture in pseudocode is sort of our intent. What do we want the program to achieve at this point? Not how do we do it. So we want to read a number from the user. We would just say something like read a number from the user. Okay? We can't tell that to the compiler, but we know what that means, read a number from the user. Okay, we'll print a prompt. We'll get a string of characters, we'll run it through scanf, we'll check the return code, we'll save it into an ampersand integer variable, all of that nonsense, right? But from a high level, we're just reading a number from the user. So we're going to try to stay at that high level. And there's no hard and fast set of rules for how you write pseudocode. It's not a rigid syntax like a real programming language. Yeah?
Can you relate it to comments in your code?
Very much. In fact, if you were to take the comments from your program, that would be a pretty good first stab at your pseudocode, right? Yeah, good observation. And when you have your pseudocode and you're writing your code, your pseudocode may be what you decide to put in your comments, right? Or can certainly help you write that, because your comments are basically what's the high level intent here. So how do we do the match picking game? So step 1, print out the introduction. It's supposed to say hello, and this is my stick picking game. And here's what we're going to do. Okay, so print out something. Don't just start staring at the user and wait for them to type something in. Okay, so be friendly in your program. So put the intro to find out how many sticks to play with. And I'm sweeping a lot of details under the rug with this one sentence to find out how many sticks you want to play with. Well, ask the user how many sticks, tell them it has to be bigger than 10. Get a number from the user, make sure it's a legal number bigger than 10. If it's not, remind them what it has to be and go back and ask again. I've got all that lumped into this one step 2. Find out how many sticks we're going to play with. 3. Ask who goes first. So this is super high level pseudocode, right? I'm not even talking about U's and C's for inputs here, but we're going to do something that basically makes the decision of who's going to go first. The next step is where it gets more interesting. Because if the user is going to go first, the next thing we have to do is ask the user how many sticks they want and subtract that from the pile. And then let the computer make a move. If the computer is going first, the next thing that's going to happen is the computer is going to decide how many sticks to take. And then it's going to ask the user how many to take. And so we've got this sort of loop where the user makes a move, the computer makes a move, the user makes a move, the computer makes a move. We can roll that into a 2-step loop. User move, computer move, user move, computer move. But getting it started can be tricky. Because if the computer is going first, we don't want the user to make a move first. We want to sort of skip down to the computer part. And there's different ways we can handle this. So one way that some people are doing is they're making 2 loops. One loop that says user, computer, user, computer, user, computer. Another loop that says computer, user, computer, user, computer, user. And they just use whichever loop they need based on who's going first. That's one way to do it. Another way to do it is to just decide, okay, we're going to make this loop as user, computer, user, computer. But before we get into that loop, we're going to see if the computer is moving first. And if the computer is moving first, we're just going to do one computer move up here. And then we'll go into the loop that says user, computer, user, computer. Did you have an idea or question? I thought I saw your hand going up. Okay. So that's another option. Another option is to have just one loop and have a variable inside that switches between user and computer. And as we go through the loop, we can say if our variable says it's the computer's turn, let's do this. Otherwise, let's do that. And then we set that variable based on who's going first, and we just keep going through this loop. And there's probably other ways to do this. And none of those is better or worse than any others. So you're going to hear me say this a lot in our courses. The way that makes sense to you is probably the best way to do it. Okay? There's plenty of time down the road when you're working for somebody else where somebody's going to say, I want you to do it like this. Right? And you're going to have to do it the way that you're told because somebody thinks that's the best way to do it. But here you've got this great creative license, right? Whatever makes the most sense to you, go with that. Because you're developing your own programming style, you're learning your likes and dislikes and preferences, right? And that's important. The more that you understand how you work as a programmer, the more successful you're going to be. So don't try to, I looked it up on Google and it said you should do this, so I'm trying to do that, but it doesn't make sense to me. Don't do that to yourself, right? Find a way that makes sense to you. And you can do that exploration at the pseudocode level. If you do it at the level of VI file and type in some code in GCC and syntax errors, you're fighting too many battles at the same time. Pseudocode on paper, it's friendly, there's no syntax errors, you're just working out your thoughts, okay, for this high-level algorithm. So I'm going to write this using that second approach that I mentioned, where we're going to assume our main loop says user computer. And if the computer is going first, we'll just do one extra thing before we start that loop. So step 4, I'm going to say if computer goes first, decide number of sticks to take, subtract from the pile, and then print the pile. So if the computer is going first, decide how many sticks the computer wants to take, subtract that from the current number of sticks, which we found out in step 2, and then print out the picture of the sticks, so that many pipes and a number in parentheses. Okay, now we're going to start a loop. So ask the user for the number of sticks to take. Subtract from the pile, print the pile, and then step 6, it's the computer's turn, so decide number of sticks to take, subtract from the pile, print the pile, and then go back up to step 5 and do this again. And that's our main gameplay loop. User move, computer move. So when does the game end? When there's no sticks left, right? This is an infinite loop the way we've written this so far. It's going to keep asking, making decisions, and going back to the top. We'd like to exit at some point. Well, the game will end theoretically after somebody takes the last stick. So that can happen here where the user's decision subtracts from the pile, or it could happen after the computer decides how many sticks to take and subtracts from the pile. So how about if right here after we print the pile, if no sticks left, then the user took the last stick, so the user wins. And then we can just exit our program. If the computer decided how many sticks to take, took that, and the pile was now empty, then the computer won. So if no sticks left, the CPU wins, and we can exit. So from a high level, does that make sense? Right? And we're making decisions here in a pretty forgiving environment, right? Especially if you use pencil or a whiteboard. You can go back and you can change this around and add to it and so on and so forth. And we've swept some details aside for now, but we'll come back and fill those in. But top level view, this is a pretty good program flow. And you've got a few choices at this point. You could go ahead and code this up, realizing that we've left out some details like asking who goes first. We got to do some error checking there and so on and so forth. Asking how many sticks, we got to make sure it's a number bigger than or equal to 10. Asking the user how many sticks to take, we got all of ODP 407 to squeeze into there, right? But we could code this up and run through it, and assuming the user doesn't make any errors in their inputs, right, this should play the game perfectly. Except maybe decide number of sticks to take. But you know, for a first cut, we could just randomize that. Or we could just say, computer's always going to take 2 sticks, right? Just to see if we've got the basic back and forth working. Because probably the trickiest part of this for most people is this idea that the user does something and then the computer does something. And wiring that up so that it takes turns and shows you what's happening after each turn, and dealing with the fact that sometimes the computer goes first, right? That's a potentially tricky part. So you could make a version that just does this, have the computer take a random number of sticks, or just take, you know, 1 stick every turn or something, and see if that works. Okay, that has a few advantages. One, it gets away from the blank sheet of paper problem, right? If you're a writer, the worst thing in the world is staring at that blank sheet of paper when you're trying to write a 1,000-page novel, right? You got writer's block. Okay, what is that for us? It's this. You're staring at you know, an editor screen, and you're trying to write a program, and no lines in buffer, right? It doesn't do anything yet. You have to create it. That's kind of a discouraging feeling sometimes. So this gives you something to write, something to get started with, and it lets you think about the high-level logic, and you can actually play it once you've got this done. And this is not a lot of Bash code. Okay, Bash is quick, rapid development. You don't have to compile. You don't have to declare variables, things like that. You can get this up and running in, you know, 45 minutes maybe, if you're up to speed on Bash syntax. And then you've got something to modulate. And in my experience, and from what I've seen of other people's experiences, it's a whole lot easier to make an initial version and then keep improving it than to try to figure out the whole final version in your head and then start writing, right? So I've said I want you to do pseudocode first, but ultimately you have to actually write the code, right? You've actually got to have the program. I would say do a high-level pseudocode, start making some actual executable code, get it running, right? And then start adding in more details. And make different versions, you know? Make stick 1, stick 2, stick 3, stick 87. Call them different things so you can go back to older versions if you like. And when you're done, just take the final version and call it stick and submit that. And you know, Git's keeping all this stuff for you, and it's free disk space and so on and so forth. So you've got stuff to use. Something else I wanted to say about this. Oh yeah, so if there's a problem here, right, you'd like to find it out before you've turned it into a 500-line program. If there's some basic logic flaw in here, like this user-computer loop isn't quite right, figure it out early. So come up with an algorithm, implement it in code, test it out, make sure it works, improve the algorithm, put that into code, test that, make sure it works, sort of build it up incrementally. And this will be a theme that comes up a lot when we're programming in C, because C, we're really going to look at taking a large program, breaking it into small pieces. And we're going to develop those small pieces by themselves. So in the C version of this, we would actually write a function that asks the user who wants to go first, right? And that function handles all of the asking again, reminding them of the options and stuff like that. Or a function that says, how many sticks would you like to take? And handles the error checking, and did you cheat 2 times in a row, and so on and so forth. And as we develop these functions, we can take those and test them by themselves. And once that function works, we don't have to think about it anymore. We don't have to think about what's inside the code of that function. We just use it, just like we use square root or printf or gets or anything else in C. We know what this thing does, we just use it. And that's going to be really important as programs get larger and more complex, and as you start working in teams, right? Somebody else will write this function, they'll tell you exactly what it does, what you have to give to it, what it will give back to you, and you just take it and use it. And you never see the code that's inside. And in spring, when we get to Java and we're working in an object-oriented environment, that's all we're doing. 90% probably of the code that we write will be other people's stuff, what we call methods or classes. It'll be stuff that's already written and supplied to us. So this modular mindset is something you're going to bump into again and again and again. So we can start working on that here. All right, how do we do this loop? How do we do step 5 and step 6 and then go back up to the top of step 5? So this is an implementation question, not a pseudocode question. This is a bash question. How would we write something in a script to get these two steps to happen again and again and again?
While loop.
Yeah, we could use a while loop, right? So in the old days, we had go-to statements in programs. We could do step 5 and step 6, and then we could say go to 5, and we could put a label there, and it would actually go there. Okay, go-tos got outlawed years ago, even though they still happen inside the computer. So we have structures like while loops. So let me show you a fun while statement. That's an infinite loop. While 1 is equal to 1, do the following stuff. It's a way to cobble a goto into your code without using a goto. Whatever we put in here is going to get executed again and again and again as long as 1 is equal to 1, which is always going to be the case, right? So this is just going to keep running again and again and again, but we have a way to get out of it, right? If the user wins or the CPU wins, we're going to say exit, and that's going to kick us out of our whole script. So it's structured as an infinite loop, but it's not infinite. Here's a cleaner way to do it, perhaps. We have the number of sticks that are left, and maybe we'll just call that number of sticks or something. So we could say something like while, and you need the $sign because we want the value of this variable number of sticks is greater than 0. Do. And now we don't need to exit from here. If the person takes the last stick, right, we can just print out a message saying the user won or the computer won. And when we come back to the top of this while loop, when we go back to here, if the number of sticks is 0, we're going to exit the while loop. And then down here, we can print a message saying, you know, thank you for playing, goodbye, and we can exit. So that's another possibility. Yeah?
Isn't going to put functions into bash?
There is. And I think we talked about it on Friday in here, and then we talked about it yesterday in the afternoon section. So function name, curly bracket, and you can put a series of things in here. And a closing curly bracket. Now if you just type the name of that function, it'll do everything that's in the function. Echo hello, print out the date, print out the working directory.
Yep.
And yeah, functions are nice because they'll let you take things that you're doing multiple times, like this piece of code up here where we do the computer's move. If you put that in a function, you wouldn't have to actually type the code in up here and then type it in down here. But we've got copy and paste, so up to you. Alright, so you can do an infinite loop and exit at the right place. You could do a loop that exits when the game is over, right? Or you could take a third approach. Make a variable, call it done or something, set it equal to 0. And you could say while done equals 0, do. And so you start your loop down here, you ask the user, you do that kind of thing. If somebody wins, what do you do? Just set done equal to 1. And eventually, done might be a reserved one, reserved word. Let's call it all done. So when you finish your loop and you come back up at the top, if anybody set all done equal to 1, you're going to exit your loop. Right? So then in here, when the user wins or the computer wins, you can print out a message and you can say all done equals 1. Or you could say, if the user wins, I'll set all done equal to 1. If the computer wins, I'll set all done equal to 2. And in either case, when you come back up here to your loop, you're going to exit your while loop. But now when you come out of your loop, you've got a flag that tells you who won. You can check all done. If it's equal to 1, you say, hey, the user won, good job. If it's equal to 2, you can say, I won, I'm superior, and so on. Yes?
So how do you go out from the infinite loop?
If it's an infinite loop, you can say exit. Right, so if you use the exit statement, that will end your loop. So let's look at an example. Alright, so I've got a variable I equal to 0, and I've got an infinite loop while 1 equals 1. And what am I going to do in this loop? I'm going to set I equal to I plus 1. I'm going to print out the value of I. And if I run this, it's an infinite loop. It'll go forever. Okay, now I've added an exit condition. Each time through the loop, I'm going to see if I is equal to 100, and if it is, then, and I'm just going to say exit. And that should terminate the script. Right, so for us, that instead of seeing if I is 100, we would say is the number of sticks equal to 0. And if it is, then we can print a message and exit. All right, questions so far? Let's go deeper. So printing the intro, finding how many sticks, that's just whatever you decide to say in the beginning of your program. Ask who goes first. Okay, so that's get an answer from the user. It's a U or a C. What does that look like in pseudocode? Oh, and let me start a sign-in sheet. Everybody's characters coming in. So we want to get a U or a C from the user. So ask user who goes first. Let's call this 1. Get the answer. If it's not a U and it's not a C, print the instructions and go back up here. So ask who's going to go first, get an answer from the user. If it's not a U and it's not a C, print out a reminder saying, hey, you've only got two choices. It's either a U or a C, and go back to the beginning. So it's another loop. So here's one way to code a loop like this using a while loop. Do this stuff first, okay? Ask who goes first, get an answer. And now let's do a while loop. While the answer is not you, and the answer is not C. Ask again and get an answer. And I'll use curly brackets just to show where the while starts and ends. So ask who goes first, get a response from the user. Well, the answer is not you and the answer is not C. Ask them again, get a response, go back up at the top of the loop. And this loop will just keep iterating again and again and again until they put in either a U or a C. If they put in a U, this will be false, right? So this and this will be false. It'll kick out of the while loop. If they put in a C, this will be false. So this and this will be false. It'll kick out of the while loop. If they put in a W, this is true, the AND is true, it's going to do the while loop again. So it's somewhat tricky going from pseudocode where we have these convenient arrows saying go back to step one to turn that into a nice structured set of statements that use something like a while. If it's an infinite loop, it's easy, just while 1 equals 1. But if it's something where we don't want to exit the program, we just want to loop until some condition is true, sometimes it's useful to take these things, do them outside, and then make a while loop that tests that condition. But again, do this on paper or whiteboard first, right? And then pretend you're a computer, right? Ask for an answer and pretend, okay, the user typed in W, so write down, answer equals W. And then decide, what am I going to do here? Well, answer is not equal to U, that's true. Answer is not C, that's true. True and true, that's true. While true, okay, I'm going to do the body of the loop, right? But pretending you're a computer is a really, really useful skill in testing algorithms that you're writing, right? It's a form of debugging, but it's higher than the debugging that we're going to work with eventually, where we're actually using a tool to debug a live program. This is debugging on paper. And I don't want you sharing code per se, but if you have an algorithm written out, it's not a bad practice to find a friend and say, hey, can you go through this algorithm assuming these inputs and see what you think it's going to do, right? And they should be able to go through and pretend that they're a computer and mimic what the algorithm is asking the computer to do. So this is another trick. When you write code, you have an idea in mind what it's supposed to do. When you look at the code, are you seeing the actual code, or are you seeing what you think the code's supposed to do? Okay, this is the proofreader's dilemma. When you're writing and you try to proofread, you're usually not actually reading the words on the paper. You're reading the words that you think you put on the paper. And so somebody who writes something isn't very good at proofreading it. You need to get somebody else to proofread it for you. So we have to play this game where we pretend we didn't write this code, we pretend we don't know what this does, and we try to look at it the way a computer would. The computer has no idea what was in your mind when you wrote this, right? So we just blindly follow it step by step by step. When you can do that, you're going to be very successful at debugging. Okay, probably the biggest impediment to debugging is looking at your code but not actually seeing what the code says, right? And this is what happens in C. Anybody ever make this typo? If not, I guarantee you will. I still make this typo. If I equals 0, do some stuff, right? Comparison in C has to be a double equal. This says set I equal to 0. and then if 0 is true, which is not ever the case, do this stuff. So every time you do this if statement, I changes to 0 and none of this stuff gets executed. And it's maddening to try to debug, right? And you can stare at this code for hours and you just see if I is equal to 0, and that's not what it says, right? So this is some practice in pretending you're a computer and trying to sort of detach what you think it should do from what it actually does. All right, we got 2 minutes, so let me just add some detail to this business of decide the number of sticks to take. So we touched on this algorithm already. If you want the computer to be able to win, so suppose you have number of sticks left in the pile. Okay, so my move just take this number modulo 4. Thanks. Take the number of sticks modulo 4, look at the remainder when you divide it by 4. So %4 works in bash just like C. If the number of moves that it wants is equal to 0, set it equal to 1. So if there's 10 sticks left in the pile, 10 mod 4 is 2, the computer should take 2 sticks. If there's 11 sticks in the pile, 11 mod 4 is 3, the computer should take 3 sticks. If there's 12 sticks in the pile, 12 mod 4 is 0, taking 0 sticks is not legal. Okay, so take 1 stick. If the computer is faced with a multiple of 4 sticks, the computer might lose. If the user knows what they're doing, they can win. So your goal is to prolong the game and hope that the user messes up. So take 1 stick. That's going to make the pile last longer, and hope that at some point the user takes a number of sticks that leaves you with something that's not a multiple of 4. As soon as you have 9 sticks in the pile, 9 mod 4 is 1, take 1 stick, you're going to win. Okay, so it's not a random number. When it's the computer's move and you decide how many sticks should the computer take the remaining number of sticks mod 4. If it's not 0, take that many sticks. If it's 0, take 1 stick. So that gets wrapped up in some code in place of this one statement. All right, and the other pieces were ODP 406 or ODP 407, basically. So think about that. Put some, if you haven't already gotten into writing this, put some algorithmic ideas down on paper. You can compare algorithms with each other. Okay, I don't want you comparing C code, but if you want to look at algorithm pseudocode, that's great. Okay, because this is really where the programming is taking place. Okay, is the algorithm development. So kick that around. We'll talk about algorithms tomorrow, answer questions, and then we're going to start looking at just practicing pseudocode. So I'm going to have some exercises, and we'll just work on them in class and compare solutions. So that'll be tomorrow's plan. All right, I will see you tomorrow then.